Hello everyone, welcome to another video of the Math Contest Club AP Calculus review series. So I hope you have learned how to solve questions involving parametric or vector valued functions. If not, please check out the last video linked in the description. So I hope you guys are up to a challenge because now we are going to be solving past free response questions on these type of functions. So without further ado, let's get started. In this question, an object moving along a curve given by x of t, y of t at time t. So instead of giving x of t and y of t, they give us dx over dt. So that's the velocity in the x direction. So this is dx dt and dy dt for time t equals to 0. So this is like the restriction. Now we have the initial conditions at time t is equal to 2. The object is at the point 6, negative 3, which is something that may be useful in the future. And note that sine to the negative 1x is arcsine x, so that's just notation. So let's start solving question A. Find the acceleration vector. So that's part 1 of the question. Find the acceleration vector. And then the speed of the object at time is equal to 2. So we recall that the acceleration vector is just the first derivative of velocity. So like acceleration is the derivative of velocity. And it's asking for the vector, so like it's going to be like in the x and y direction, something like that. And what about the speed of the object? So we can recall that the definition for speed is going to be this. It's just like let's just say it's the velocity of the object. Like you have to add up the two components in the two directions. So it's defined as this. So those are the hints for the question. And here is the solutions. So at time t is equal to 2, we first, for the acceleration vector, we just take the derivative of velocity x and velocity y. We plug in the value t is equal to 2, and then we obtain these two values. So we just put them into this acceleration vector. And similarly for speed, we just plug in the values and then we get 1.208. So that was part A. Now let's look at part B. We find out that the curve has a vertical tangent line. So we know that a tangent line is just dy over dx. What does it mean when the tangent line is vertical? Well, it means that dx is 0. So we just need to find the value of t when dx over dt is equal to 0. So in other words, you want this expression to be equal to 0. It may look like a complicated expression. I mean, you can still do it by hand, but this tends to be like a question on the graphing calculator section. So you can just graph it and use the 0 function to find it. So this is the answers of how it's done. So we find that the answer is when t is equal to 0.693, which convenient is also when the t is equal to natural log of 2. Okay, now let's move on to question C. Let m of t denote the slope of the line tangent to the curve at x of t over y of t. And we need to write m of t in terms of t and evaluate the limit of this as it approaches infinity. So as we have stated in B, the tangent line can be found with this expression, dy over dx. So in order to solve this question, we just put dy over dx over dt. So we just have this expression, And then we can turn it into a simpler fraction by moving this into the denominator of the first one. And we just can find the limit of this expression as it approaches infinity. So the limit of this is going to be 0. So 1 minus 0 is going to approach 1. And it's because like limits commute with continuous functions. So it means like you can move the limit like inside. As long as it's continuous, it commutes. So it works basically. So this expression is basically equal to arc sine of 1, which is pi over 2. So it's just a constant. And then when we analyze this limit expression, if this is 4t, this is a constant, and this is 1 plus t squared. The power of 3 dominates over the power of 1, so this just approaches 0. So in conclusion, the slope approaches 0. Okay, that was C. And now let's look at D, the last question. The graph at the curve has a horizontal asymptote at y is equal to c. So we want to find an expression involving an improper integral that represents this value c. How are we going to solve this? Well, we just want to, since it's a horizontal asymptote, it's going to look like something like this. So it means that as x approaches infinity, or even t approaches infinity, then because we know that if t approaches infinity, there will be an asymptote, because asymptotic behavior is observed when like functions reach arbitrarily large values. It tends to flatline. So we just need to put in this and then try to find the limit as t approaches infinity y of t. And how can we find y of t? Well, we can just integrate this function. But we don't know the initial conditions yet, but we find out that it's over here. So the initial condition is like -3 at t is equal to 2, and then we take the integral from 2 to infinity dy dt. So what does this look like? Well, it's pretty simple. So basically, it's just saying like t approaches infinity. It needs to reach like arbitrary large values for y to flatline, because that's basically what the asymptote is defined as. And then we are trying to find y of t with the expression like this as the initial condition at t is equal to 2, and then you add this. So that was it for the first challenging question. And let's move on to the next one. Okay, if you want, you should consider pausing this video and trying out yourself and come back later. Okay, I assume you have came back. Let's look at the question. Over here we have a particle moving along a curve, and there's another vector valued function like x of t, y of t. This time they gave us x of t, y of t is not explicitly given. And this time they have units, it's meters and seconds. And we also have what's dy over dt. First we find the speed, and we know from the last question that speed is just equal to the square root of vx squared plus vy squared. Just think of Pythagoras. And we have velocity of y, that is basically dy over dt. But we don't have vx, we only have x of t, so we just take the first derivative. So this is how we took the first derivative of x of t, and then we just plug in the numbers, and then we find out this is the speed of x at t, speed of the particle at time equals to 3 seconds. Now let's find the total distance traveled by the particle between the time is equal to 0 to 4. And because this is a two-dimensional sort of this movement, and it's distance traveled, so we need to find the arc length. So we just use the arc length formula, that's this one. The arc length formula was previously explained in another video, and I'll link it in the description, so check it out if you are not familiar with it. But basically, we have x prime of t over here. Y prime of t is just this expression. So we just put this in our graphing calculator, and this is the arc length or distance traveled we obtained. Now let's move on to part C. So during this time period, there is a time when the line tangent to the path is horizontal. What does this mean? It means that the slope is 0. So dy over dx is 0, so that dy over dt is 0. So we can just set this expression to be equal to 0 and plug it into a graphing calculator. We find out this is the time. Okay, so then we notice that there's another part of this question. Now it's trying to ask, is the direction moving towards the left or the right? You may ask, what about up and down? Well, if the line tangent to the path is horizontal, it means that the speed vector is only like horizontal. There's no vertical component. So this question makes sense. We just need to plug in this to the x prime of t formula to find like the direction of velocity in the x direction. And it's positive, so it means that it's to the right. Because like given by convention, if it's something is positive, it's moving to the right in the x direction. And if something in the y direction has a positive speed, it's moving upwards. Okay, so this was question C. Now let's move on to question D. There is a point in x with the coordinate 5, which the particle passes twice. So how are we going to find the values of t when this occurs? We have an expression for x of t that is here. So we just set this to be equal to 5, and then we solve the quadratic equation. So now we have two values for this. Next, what's the slope of these lines? Well, we can write up an expression y prime of t over x prime of t just to find the slope. And then we can plug in the values into this expression, and we find these slopes. Okay, now to the last question. What's the y coordinate of this point? And we are given the initial condition, y2 is equal to 3 plus 1 over e. So we can just use the expression y of, let's just say an arbitrary x is equal to y of 2 plus 2x dy dt. This is like a net change formula. So we just put the values in. Since 1 is smaller than 2, if it makes more sense to write it this way, we can just put the integrand this way. So this is the accumulation of change. This is the final position, and this is the initial position. We plug in the values and solve. Y of 1 is equal to 4. And it's similar for 2 and 3. Just notice that the bounds are different. This time it's 2 and 3. But we find out the answer is actually also 4 meters, which is really interesting. Okay, so that was it for the two challenging parametric or like vector valued questions, AP staff response questions. I hope you learned something new, and if you have any questions, feel free to leave them in the comments section. Thank you so much.